Numerical differentiation. I want to show you guys the use and the big pitfalls of numerical differentiation. I think you guys have already experienced it, at least some of you, in the context of the computational multiphysics, but I'm going to show you guys exactly what's happening here. I'm going to show you the forward, backward, and central difference methods. Do any of these sound familiar to you guys? Some people have heard a little bit, at least like in passing, right? So here we are, we're gonna derive it and show you exactly what it is. And justify the use of some of those methods in terms of the order of accuracy of the approximation. So way back to the first lecture where we talked about the accuracy of truncated theories and things like that. Okay. So numerical differentiation is a method to calculate the derivative of a function. Wow. We've already kind of approached this in the context of a secant method when we were talking about the root finding and the optimization methods. What we're basically going to do now is kind of formalize that. And to be entirely honest, I might teach numerical differentiation as one of the earlier lectures moving forward, because it kind of makes sense to talk about this before talking about like the difference between secant going towards tangent methods for root finding and optimization. But alia iacta est. So the idea with a secant is quite literally, if you have 2 points, you connect those points and you draw the line, and there is your secant, where secant is defined as a line that connects between 2 points on a curve, right? As Q approaches P, your secant approaches your tangent line. So your tangent line is kind of the real goal for a lot of these methods that you want for optimization and root finding. This is how you do it numerically. Most methods, we're going to be expanding our approximations in terms of the step size, which is the distance in X between P and Q, right? And you're going to see we're also going to have it on the other side, and we're going to have an even step size going all the way across. Okay. So this notion, this picture kind of motivates the idea behind the forward difference method. What we're going to do is we're going to take the ever useful and humble Taylor expansion of f of x at a point x with step size h. So this should come as no big surprise to you guys. F of x plus h is equal to f of x plus the first derivative times the distance plus the second derivative, distance squared, over 2, and the third derivative, h cubed, over 6. There's going to be a fair bit of math that's going to be flying at you here. Pay attention in particular detail to the powers of h. That's going to be my help to get through the rest of the parts here. Okay, we're going to truncate. This should be ... because it doesn't actually end there. Okay, we're going to truncate it after 2 terms, which means that we're literally, right, this is our order n notation, except this time we're doing order h because h is the step size. That's our parameter that we're doing here. So after 2 terms, you get blah, 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 plus order of h squared, and then we literally just solve for it. We just say, okay, f primed is equal to approximately this plus some other terms that are order h squared. As a reminder about the big O notation, you don't worry about positive or negatives. You don't worry about anything else. So we're not worrying about like h cubed, 4th, 5th, 6th, 7th, 8th. All we're worried about is that leading term there. And that's going to give us the order of approximation. So the next iteration, the next best guess for this is going to be proportional to h squared. That's the whole point. I'm going to be using this example of rocket velocity to illustrate some of these topics. So here's the equation for the velocity of a rocket, and we want to know what the acceleration is as a function of time. So analytically, because we have the analytical form, we can just do that, right? But the whole point is to work out numerically, and we want to compare it to the analytical answer. Excuse me. Okay. So here is the function definition. Yes, I trust it. Blah, 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 right? Simple function definition. Here's the acceleration already worked out. And what the first thing that we want to do is just look at these things. So nicely and kind of conveniently, it actually is approximately linear. In general, of course, you won't have an answer or a function that looks quite so clean. You're going to get much more messy functions. They're going to be convex or concave. You're going to have to deal with a lot of fun stuff. Okay, but this is a nice example. So the forward difference scheme is super easy to implement. Actually, they're all pretty easy to implement. Literally, so what we're going to do first is talk about the case where you actually have a function that you can call. right? Then we're going to move on to the case where you don't, and you just have a list of variables and a list of values that they're evaluated at. Assuming we can actually call the function, right? We literally just evaluated at x plus h minus f of x divided by h. That'll give us our answer, and then we can tune this parameter of h to be whatever we want. And when we graph it, we get the plot that I just overwrote. Okay, so the analytical answer is the one in red here, and you'll notice that, sure enough, as you shrink the step size, you get closer and closer and closer to your answer. Great. Notice that you're going from the top in, from the top down. By contrast, we could also do backward difference. And the idea with backward difference is that you just reverse the direction of h. So instead of stepping forward, forward difference, you step backwards, backwards difference. You get the same equation because you're ignoring the negative signs on the order notation. And again, you solve for f primed, and now you get the same thing, but instead of stepping forward, now you're stepping backwards. You do that, and Now you get almost the exact same behavior, which shouldn't actually be a surprise because that curve is so gentle. But now you're coming at it from the bottom up, right? And again, when we're looking at this sort of thing, like you see one technique that's overshooting and another technique that's undershooting, what do you think we're going to do? Split the difference, right? Split the difference, average, what have you, central difference method. The idea with the central difference, and this is, I really like this because this is one thing that like we're going to exploit something pretty cool that happens. Pretty cool. Math is cool, right? With these discrete representations that you wouldn't actually kind of like normally expect. So what we do is we do the forward difference, we do the backward difference, and we subtract them. So literally what we get is f of x plus h minus f of x minus h equals to 2 times this, proportional to h, and then we get a term that's h cubed. And then we go h to the power of 5. So what's happened by subtracting the difference between the forward and the backward, we're canceling out even powers of h, which is pretty cool because if you truncate it to only the first couple terms, you actually get a second order accurate derivative approximation just by looking in front of you and behind you. And notice we're not even evaluating the function at the point of interest, right? Which is kind of funny when you think about it, right? But there it is. And the nice thing about this is that it's second order. So you're gaining an order of accuracy without doing any additional work. You're still doing 2 function calls, which is great. When you do that and you do the central difference method, I had to do this so the orange line here is forward difference with step size 2. The blue line down here is a backward with step size 2, and central difference is this dots. I had to make it into dots because it's exactly overlying the analytical solution. That looks super awesome, amazing. In general, you won't get quite such good agreement, right? Central difference is better. It is categorically better than forward and backward difference, but it's not a magic bullet, right? You will not in general find the analytical solution. It's just in this case, it comes out to be very similar. Okay, so let's see what's happening here. What I did here was subtract. So I took the acceleration, which is the first derivative, for the forward difference, FD, step size 2, minus the analytical answer. So that's the error, right? That's the error in the forward difference, the error in the backward difference, and the error in the central difference. And I'm only plotting it for the first 4 data points here, just so, because otherwise it's too long. We want to be able to see this thing. Okay. And then we're going to decrease the step size from H2 to, from 2 to 1, and we're going to replot it. For the forward difference, you can see that by decreasing the step size, so again, decreasing the step size, you're doubling your sampling frequency, right? By having the step size, you have the error, right? Because it's order it's linear order accuracy. Right? Same thing with the backward difference. You're just having the error, but when you do it with the with the central difference, first of all, it starts off lower. Don't be too preoccupied with that. It's like when we looked at the computational complexity. Don't get hung up on the speed of execution. What's more important is the behavior as you're changing one of these approximation parameters. So as we go from 2 to 1 in step size, you've actually divided the error by a factor of 4. That's your squared order accuracy kicking in and shrinking that down, which is really nice. Yeah, so it finds a more accurate solution in the same number of function calls, which is super nice. It becomes more accurate with step size quadratically, which again, like if you want to find a better answer, but you want to balance off the computational cost, that's obviously better. The problem with this one is that you have to be aware of the boundaries, right? For interior points, that's not a problem, but if you look for the derivative at the boundary over here, you're not going to be able to take step size minus h. Similarly, over here, you're not going to be able to do that. So guess what? Forward difference, backward difference. That's why we're still talking about this. By the way, this part's nice because I actually get to like talk about what's actually done. You know how like I presented a bunch of theory and then said, well, this isn't actually done because it's been superseded by this, right? We're actually going to be doing this. You guys will actually do this in the future. Hallelujah. Okay. Any questions so far? Pretty basic. Excellent. We can do the exact same thing in expanding to higher order derivatives, right? And the interesting thing is that once we've got those expressions, we can substitute that in to the linear equation, to the first derivative, and use those to improve the first derivative, right? The first derivative had order n, and then we truncated it after 2 steps. Well, if we have an approximation for the higher order, let's use that and let's get a better approximation. So let's see how that works. Again, consider the Taylor expansion. Now we're looking at f of x plus 2h, right? You write out your equations. Recall, we already worked this one out. And again, we're doing the subtraction of the second one. So this one minus twice of the first one. We get this, and now we can solve. So the idea is that we're eliminating f primed. That's what we're doing by subtracting these. Sorry, this should be, yeah, twice the second minus the first. So we're eliminating f primed, and we end up with an equation for f double primed, which is nice. And this becomes order h, right? So we're sensitive, we're kind of sensitive to this thing again. But we can still evaluate this because it's again forward difference. We're taking one step forward. So we're taking the function value, then we take one step forward and we take 2 steps forward. So if we're at the boundary, we can't go backwards, but we can go forward twice, which is nice. We could also do the exact same derivative in a more recursive fashion, right? So what we could do here is, if we had one data point here, one data point here, one data point here, we could also say, what is the derivative here by forward difference? Okay, it's that. What is the derivative here by forward difference? Okay, it's that. Second derivative is going to be the derivative between the first derivatives. Does that make sense? You get the exact same answer. I don't know why this method is more common used as the derivation. This also makes sense to me. Maybe it's not so clear what happens with your order of accuracy. So that's why it's generally preferred to look to Taylor. The nice thing about this one is that it lends itself to recursive programming, right? Doing the recursion for this is very straightforward. You're just doing derivative of derivative of derivative. So if you look at the, I think it's the, I don't remember if I talk about it here or not. I think it's the numpy diff function is doing recursive derivatives. That's how it works. That's how it gets you those values. Okay. So given that we now have an approximation for the second derivative, we can go back to our original equation and plug it in, right? F of x plus h, f of x, f prime times h plus f double prime times h squared over 2. And then now we have order h cubed. You plug that in, you turn the crank, and lo and behold, now you get an approximation for your first derivative, which is second order accurate, which is great. We like that. Notice that when you're moving these h's around, so there's a little bit of a trick here. You see, if you go through this math, because this h gets divided through, you end up reducing the order of the approximation here, the big O notation. So just do be aware that that's how it works. That wasn't a typo. It does go from order h cubed to order h squared, and that's because you're dividing through by h, right? If you have a quadratic that's leading order h cubed, you divide through by h, obviously you're going to drop a power. Notice, however, that we now need 3 function calls in order to evaluate this. So yes, we do have a higher order accurate approximation, but we have paid an expense because now we need to evaluate that function once more. If we're just doing like a simple function call, no problem. If we're doing an optimization with a multiphysics something, every one of these function calls takes, I don't know, 2 hours on an HPC to solve. You know, we want to get the most bang out of our buck on this. So maybe we don't want to do this. I'll come back to that one though. Being a mathematical formula, of course, somebody has generalized this, and this is the order approximation. So the packages that work on this, instead of doing it recursively, they'll just use this function. This is n choose I. I don't even remember how to do this. To be honest, I would have to look it up. But this is the algorithm by which you can generate arbitrary order accuracy. But again, you're using increasingly more data in order to get that answer. So let's compare the error for the improved forward difference model. This is forward difference 2. The implementation is literally just what we wrote up top. Okay, so this is for H2 and for H1, and let's compare it against the vanilla forward difference. So between the original one and the improved one, first of all, you notice that the sign has switched, which is interesting, but not really so important, to be honest, because the absolute error has decreased, which is exactly what we wanted to see. Similarly, for H1, what you can see is the difference between, oh no, sorry. This is, yeah. So what you see here, though, is the, whereas for the original finite difference, for the original forward difference, when we shrunk the step size, when we cut it in half, we only improved the answer by a factor of 2, right? We only half the error. With this one, when we compare between h is equal to 2 and h is equal to 1, we can see again that we get that nice quadratic error improvement, which is pretty cool. Central difference is over here. This is same for the same step size h2. So it's kind of neat because even then, even with the improved version, central difference, which again only needs the two function evaluations, is actually still comparable. I'm not going to go through the derivation. It basically follows exactly the same for the backward difference. There it is, second order accurate first derivative, and generally same thing for the central difference. You just follow the same algorithm. You subtract the two, you cancel out your terms, and there you go. Second order accurate first derivative is this one, which kind of gets a little bit messy, but actually still basically amounts to the same thing. Notice how now we're doing 4 function evaluations instead of 3. So when we were doing forward difference, right, to get a better first derivative, we would have to do 3 function values. For central difference, now we have to do 4, but our order has also increased. So we've gone from order 2 to order 4, which is again a whole lot better. Any questions, or maybe I'll summarize this first. So the idea with forward difference is, so here's our nice curve here. This is the function that this is the point that we're actually trying to evaluate, xj. That's our true slope. Forward difference looks forward. Backward difference looks backward. Central difference is between, which counterintuitively actually gives a better answer than any data that actually uses that data. We could improve the accuracy of the approximation by decreasing the step size or by approximating the higher order derivatives. Generally speaking, there's like kind of the engineering mindset. It kind of looks at this and says, well, come on, like you want to use the best order accuracy that you can for the data that you have. And what that would mean is that we would want to use option number 2, right? Because that way we're getting the most bang out of our buck. In practice, we don't actually. In practice, we want to reduce the step size. And there are reasons for that have to do with the ability to represent those gradients. So if you have a function that's doing something like that, right, which is perfectly reasonable function. If you had a step size that was like that, you might actually just think that this is flat, which is not the case. And in order to resolve it, you would need a finer step size, even to be able to pick up that there is something else going on there. And typically, because we don't know what shape of function it is, the general course of action is to refine your step size so that you can resolve those gradients at all. The actual explanation for all this goes into Fourier decomposition to something called the Nyquist frequency, which is the frequency that you are able to pick up in your signal for a given discretization. And past your discretization, your sampling frequency determines how fast you can pick up or what frequencies you're actually sensitive to. So you could consider that function to decompose into Fourier space, and then it kind of makes sense that you want to get as small a step size as you're able to get in order to pick those up. Shoot. Mm-hmm. Say again? Yes. Yes. You absolutely could, right? And the correct algorithm in that case, if you were just evaluating at a single point and you wanted to get a good a derivative as you could, right? Then that kind of lends itself to an algorithm, right? You evaluate it based on one step size, you have the step size, you evaluate it again, you do that as many times as you want until you've reached some kind of relative threshold, relative tolerance, which you absolutely could do. If you are only interested in evaluating the derivative at a single point, that's fine. This is actually setting the stage for finite difference method for solving PDEs, in which case what we're going to be doing is discretizing a domain that goes for a certain interval. And yes, you could do, massive refinement, but your memory requirement for your computer is going to go through the roof. Right? Ideally, I mean, continuous is infinitesimal sampling, right? That's the definition of continuous, but it's not practical in reality. Yes, yeah. What do you mean shifted? Yeah, yeah. You mean like that? But why wouldn't you just use central difference at that point? Okay. It does. It makes sense, but it's the whole point with the central difference is that you're relying on the fact that you're going above and below to cancel out those even powers. And if you're not, so the optimal answer, so if you did that and you put it into an optimizer, what you would find is the optimal answer would be 1 over here and 1 over here, in which case you're back to the central difference. Because it's at that point where any kind of uncertainty before and after cancel each other out. Make sense? Excellent. Okay. What do we do for discrete data? So if I gave you, hey, look at this, a function, right? x1, f at x2, da, 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 da. How would you do that? Anybody? I give you a list of x coordinates, a list of f values, and I ask you to tell me the gradient. I'm going to go to the peanut gallery if nobody puts up their hand. I've got requests for Pikachu. Stephanie there? No, he's playing quiet now. How about Jason? You there?
Yeah, I'm here.
All right. So what do you think you have to do if you have a discretized function? So you have a list of x coordinates and a list of f coordinates. Is the sound coming through just here, or is it? Oh, hold on 1 second. How do you do this? Okay, try that, Jason.
Test.
Yeah. Okay.
Okay. So we got a list, and we want to find the gradient. You said.
Yes.
Well, the gradient is in a matrix. It's the derivative of all the rows with respect to whatever the variable is. So, like in this case, it would just be the derivative of that.
Well, yeah, but how would you find the derivative?
Well, we can use central difference, or we can use a central to find it.
Exactly. And your step size?
Like 2 to start, but if it doesn't work, smaller step size.
So in this particular case, you no longer have your function value. You no longer have your function that you're able to. Is my microphone on? Yeah. You no longer have your function that you're able to call whenever you want it. So you've got a fixed sampling frequency. In which case, your step size is just going to be the distance between your samples here. Does that make sense? Yeah. I'll come to that one. You lament. Yeah, I'll show you. Okay. So the nice thing about the numerical finite difference method is that it's actually it generalizes to discrete data very nicely. All you do is you just set your step size to be equal to whatever your sampling frequency is, and hope and pray that it is evenly spaced. Because if it's not evenly, then it gets messy, is the short answer, James. You do have to beware of your boundaries, because central difference, you can use this point. Okay, so you had a question about how to do that, right? I thought I had a good one here. Here we go. Look at that. Okay. So for data here, so this is an example of like your discretized function, right? You've got your x values, x naught, 1, 2, 3, blah, 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 through to xn. You're bounded by a and b. You are not bounded in the sense of optimization. This is your boundaries for your list. Give me 1 second. And then you've got these function values, y naught, y1, y2, blah, 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 blah. If you are asked for the derivative of this function and you wanted to plot the derivative over the entire domain, what you would have to do for any of these points in between, you would just say f of x plus h. So say you wanted to know the derivative at x3. H is whatever this interval is here. So all you would do is say x3, x4, x2. All you would do is you would take x4 minus x2, excuse me, f, we're using y, y4 minus y2 over 2h. So this becomes your step size, h. That's y4, y3, and y2. Does that make sense? So now, because you only have discrete data and we're assuming that it's evenly spaced, your step size just becomes that interval, and all you can do is just call the point after it and the point before it. Question, Ethan. Come to that one. You guys are chomping at the bit here. It's good. We're excited. We're moving here. Well, that's a whole different question. Those are two questions, and I would postulate a third, which is, should you do that? So all of those answers and more are right after this. Okay. So in the interior points, the correct answer for working out the gradient is going to be, what's the best one? Central difference, right? At this point on the boundary, you do not have y negative 1. Doesn't exist, wasn't sampled, before the beginning of the universe, I don't know, but you don't have that. So at this point, you're going to have to use the forward difference, and on yn is the backward difference. Good. That can be confusing. So rather than try and do that, we just rely on the NumPy implementation. This is this is an example of discrete data. It looks like a parabola. Spoiler alert, it is a parabola, right? That's your x values, that's your y values. Okay. If we apply just central difference, we would have problems, but NumPy has this great tool called gradient that identifies the endpoints and treats them with forward and backward difference as required. So say we thought this was a parabola and we wanted to prove it using the gradient. We're expecting a straight line, gradient, right? First derivative, okay? So using NP gradient, we evaluate that and we get that. Anybody guess why this isn't a straight line? You got it. The order of accuracy at the endpoint. So if you look at the documentation, it has this very nice feature, edge order. Guess what edge order does? It applies the second order accurate method. We put that in, and lo and behold, we get the orange line, which is a perfectly straight line, and therefore, yes, this is going to be a quadratic. This is quite literally the foundation for the finite difference method. Finite element method is a bit different, works off integrals instead of derivatives, and there's a very good reason why, and we'll get to that right afterwards. Any questions that aren't about unevenly spaced data? Okay. Unevenly spaced data. When it is not evenly spaced, we can always do first order. Always exists. We can always work that out, but like we're limited to the degree of accuracy, right? And there are other problems with that too. Generally, what we would want to do is fit a polynomial locally and then take the derivative of that polynomial. The classic way to do that is good old Lagrange interpolation. It has an analytical form. We can take the derivative. You get this expression. And that actually converges to the central difference when you have evenly spaced. So this, in a lot of ways, is the generalization of that central difference formula, and which probably relates actually to your question about the unevenly spaced data too. So you can actually do that and then use that fact to get the data. It actually has comparable accuracy too, which is kind of nice. The problem with that is how you go to ND, right? This is great for 1D. Going to general case is a bit different. We spoke kind of at length about how you would fit a polynomial, right? We talked about the issues with continuity. So for example, if you have 3 data points here, 1, 2, 3, you can fit a polynomial, that's fine. You can evaluate the derivative at all of these points, no problem at all. But now you have a point data that goes like that, and now you fit the polynomial like that, and now you have a discontinuity in your slope, which is going to be a problem. Where actually your function looks something like, I don't know, like that. Right? So this goes into the whole, well, let's do a cubic spline fit. Right? Now we're fitting that, and we're saying that it has to be continuous. Again, we get into problems with generalization to ND, which, spoiler alert, is where we're going. Okay. The other problem with this is what we do with uncertainty. I'm going to shoot for the whole lesson here. Let's see what happens when we introduce error. There was a question, a discussion earlier in the lab about using optimization for the computational methods, computational multiphysics course. And apparently there was a case where there was a lot of variation and people couldn't rely on the gradient. This is why you can't rely on the gradient. Okay, so let's introduce a new function, which is error, which is the velocity plus this random sampling of error. We calculate the error, we calculate the derivative using our best answer, which is central difference. And then we're going to plot it. This is the original curve, which is the orange. Or excuse me, the blue here is the original curve. The orange is the noisy curve. And you can see that they're essentially identical. You can't even see this thing. This is on the order of, what is this, 1,000? Hundreds? And we've introduced noise on the scale of 1, right? So it should be 1% accurate, at least in velocity. We do the difference and we get a super messy thing, right? If we up this, make it a factor of 10, we get kind of a noisy signal and oh my God, what's happening here, right? The problem is that differentiation tends to amplify error. And what's happening there is, I'm going to switch this back to 1. Otherwise, it's going to mess up my my analysis later. What we have to do is consider the Fourier analysis of the signal. If you consider it like that, you've got this long wavelength signal that's varying over the course of 0 to 30, which is our total sampling interval. But our noise is happening at a frequency of the sampling. Does that make sense? Right? Because you've got one thing that's real, that's the long range one. And then you've got this thing which isn't actually real. Like it's real and experimental, but it's not real in a mathematical sense. It's just this random perturbation. But the problem with this is that you shrink your step size and now you get even higher frequency noise. Right? So it's kind of hard to get away from this thing. If we look at, because we're in a Jupyter notebook, and we all know what Fourier transform is, we can do the Fourier transform of the error, right? So this is V of t minus V error. That's our noise. Let's do the Fourier transform. Let's look at this. What you see here, no, this isn't a course on Fourier transform. I won't go into it farther than this. Just to say that this is our longer range signal way over here. And you get all this noisy gobbledygook at exactly a period of 1, which is our sampling frequency. If you cut the sampling down, that entire noisy mess is going to shrink down. The problem is, the higher frequency your noise is, the larger your gradient is going to be. Right? That's why you shouldn't be doing this on noisy data. What do we do? We've got 2 minutes left. Any ideas? Lightning round. Anybody online? You got a question? Yeah. Got an idea? Come on, man. Anybody? Fictitious bonus points? Complex bonus points? All right, we're out of time. There are a few options you can use. Basically, the idea is to get rid of that high frequency noise, right? What do you do with high frequency noise? You smooth it, right? You can smooth it. You can pre-filter the data. You can do a moving average, low pass filter. All of this signal analysis is coming into play now, right? You could regularize the derivative. So this is kind of like the spline thing. What you do is you say that the derivative here has to be almost the same as the derivative right beside it. So if the derivative is doing one of these things, you say, no, 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 it's got to be a lot smoother. And now you work on this continuity to exploit that to actually get a better result. Do that. You could also do a Svidsky-Golay filter, which is doing a linear least square to fit a low degree polynomial. So take 5 points, fit a cubic, take the derivative of that, and now you've got a much more well-behaved derivative. And then you just do that in a moving fashion to get farther and farther and farther. Or the last option is to integrate instead. The idea with this is just like the derivation amplified that error. I see we're over time. The derivative amplified that error. Integration works the exact opposite. You end up essentially summing over the pluses and the minuses, and they cancel out, and your integration is a lot better. That's next week. Actually, it might be tomorrow. It might be Wednesday at this rate, because otherwise we're done this. The idea with that one is that you integrate your signal and then you fit it to the integral of whatever you think your derivative should be. You could even just integrate it flatly and then do the numerical derivative of that, which will recover your signal, but in a much more smooth curve, in a much more smooth form, and then you could even do the second derivative on that one. All kinds of different ways to do. Very, very quickly, higher dimensions, this is trivial. All you do is you literally take the components of your gradient and you do central difference or whatever difference in either of those ways. The derivative in x is that way, y is that way. You talk about stencils, you might get into that sort of thing. We're not going to talk about those until we talk about time-dependent partial differential equations. Nice thing about that is that it's even more general when you get up to a boundary, right? If you're doing a two-dimensional discretization like that and you have a boundary, you can combine forward difference this way with central difference this way. And you can still get the value there or here. You can do those two and you can do forward difference to get the gradient there. Generalizes very, very nicely. Here's a quick example. I'm over time. There's a nice plot and it shows some arrows on it. That's it. That's all I got. If this ever works. I don't know what's going on there. Yeah. So there's a messy function and you just finding the gradient is super trivial with that. Yeah. Ooh, that's messy. Any questions? Okay. So spoiler alert, that was the entirety of numerical differentiation. So I might start talking about numerical integration on Wednesday. And then Thursday, we have the review and we'll take up the assignments in preparation for the midterm. I will post all the information about the midterm on the channel and that way everybody will have it. See you Wednesday. I know. Sit still because I finally get to talk about the real stuff. This is actually what we've been building towards. This should actually be like 3 weeks time, but I brought it in here because I think it might help you guys like cement what we're actually doing before this point too. So the goal of today, 20 minutes, apply the finite difference method to solve steady state differential equations. Hallelujah, real world problems. Be able to implement Dirichlet, I think I misspelled Dirichlet, and Neumann boundary conditions. Do you guys know what that means? Dirichlet and Neumann? No worries, I'll come to it. Okay, apply linear system solution methods to real applications. We're actually going to use these things. And use our root finders to solve nonlinear equations. Hooray, right? Okay, so in the past lecture, we saw how to write derivatives in terms of the elements of a list, right? So the derivative here depends on these two values. The second derivative depends on these three, right? On one side, it goes like that. On the other side, it goes like that, okay? So let's use that. So let's take an unknown function. I wrote f, and then immediately for the rest of it, I'm talking about y's. Sorry. Take an unknown function f. We discretize it by sampling it at a set of coordinates. We saw that finite difference basically only works realistically for when we are evenly spaced. So let's do that. Let's use a step size h. Okay, this is our old example. This is from the online textbook, right? What we've got is this function y, and we're sampling it at x0 up to xn with a step size h. And what we're doing, what we're asking for is what is y0, y1, y2, y3, y4, blah, 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 blah. That is our vector of unknowns, right? We've heard this terminology before. Here's a nice summary table of the different techniques. That's how you calculate the derivatives. I'm sorry, this is really small. Markdown tables are really messy for some reason. I don't like them at all. Okay. Right. Let's look at a problem. Rocket trajectory. We're going out to launch a rocket. Let y as a function of t, right? So our x-axis here is time, be the altitude, meters above the surface of the rocket at time t. Hooray. We know gravity. Gravity still applies. Good. We have F is equal to ma. Also good, right? Right? We're getting places. So we want to have the rocket at an altitude of 50 meters after 5 seconds. T is 5, y is 50. Okay. What should the velocity be at the launch? How much gas do we need to give this thing? And we're ignoring air resistance because we're physicists. Eng phys, right? So the ODE, super simple. Second derivative is equal to negative acceleration of gravity. Let's write this in terms of our finite difference. So here's where the magic starts, right? We get a second derivative. You can refer back to that table if you want, or you can just memorize it. It's not that hard. Or just ask Gemini to do it. And this is what you get. This expression only applies to the interior points, right? Because it's a central difference, so it only really makes sense to talk about it for y1, y2, y3, y4, not for y0, because there is nothing on the other side. So what we have to do is apply, in this case, boundary conditions. So there are three types of boundary conditions, actually. There's Dirichlet, which is when you say the function has a value at that point, and it's super simple to put into finite difference and also finite element method. You just say, y is this at this point, right? So we start off knowing y0 is equal to 0. And y10, which is our 10th element in our unknown vector, is equal to 50. Okay, so I'm expecting people to get tripped up a little bit there. So I'm going to repeat that one again. Our time range goes from 0 to 5. But we're dividing that, we're discretizing that into 10 steps. So first of all, that actually means we have 11, right? We have 11 t values and 11 y values because of, what is it, cardinal versus ordinate number system, something, right? We get 10 steps, so you add on the endpoint, you get to 11, right? So this is y10 is equal to 50. And what we do, well, this looks pretty familiar, right? We've looked at this sort of stuff before. What is this? It is a linear system. What do we do with linear systems? Right? We put it into a matrix. And then what? We solve it using, you got it, LUD. Somebody's been studying, right? If anybody didn't follow that, study more. This is pretty simple to work your way through. All you have to do is just like literally apply it line by line to build this matrix. This one can be a little bit messier to get this your constant vector, your b, in our linear system parlance. Just remember to keep all the terms that have y, your unknown, on the left-hand side, everything else on the right-hand side, and you'll be fine. Okay. So this is a code. It gives us the matrix A and B. First thing we have to do is work out our step size depending on the number of elements that we want, our discretization. Here I said 10, so we're going to get a step size of 0.5. This is just building that matrix. So it looks kind of messy, but it's actually super simple, right? All we're saying is A at 0, 0, that's our top diagonal, is equal to 1. You guys know why? This equation, right, is y naught is equal to 0. So there is a 1 on the diagonal, which is corresponding to y naught. And then over here in the constant vector is the 0. So when you multiply this through, 1, 0, 0, 0, 0, 0, y naught is equal to 0. Right? Same thing on the bottom. On the bottom, we have y10. So again, it's a 1 on the diagonal. 0 is everywhere else. And this time is equal to 50 on the other side. So when in doubt, multiply through and you'll see it. You'll see it real easy. Okay. A00 is 1. ANN, which is the bottom right-hand corner, is also 1. And we're going to build our constant vector over here, but you can already see that it's 50 down at the bottom here. Then you say in everywhere else, you go along the diagonal and you say whatever before and whatever afterwards. So every row that you go down corresponds to another element in your vector of unknowns. And you're basically just applying that stencil from the finite difference to that matrix to build it up. That's how this works. You get -2 along the diagonal because of this term. You get 1 from this one, y minus I minus 1, and yi plus 1, you get another 1 over here. Everything else is 0, which should already raise some bells. Let's see it. Okay, let's actually solve this thing. Hooray! So I didn't have to restart my runtime, right? So we're getting the matrices, we're plotting it because it's always nice to plot these things, especially when it's super simple, right? You can see the matrix. This should already be raising flags in your brain, by the way. It is symmetric, and it's actually not symmetric. It looks symmetric, but it's not symmetric. You can see at the endpoints there. Yeah, it looks like it should be, but it's not. Yeah, I know. Sorry. There are ways to make it symmetric, but that's a whole nother topic. Okay, the B vector is here, and you throw a solver at it, and lo and behold, you get something that looks like a rocket trajectory. Whenever you get a result like this, take a look at that plot and make sure it actually makes sense. So what are our boundary conditions? The easiest things. T at 0, the height is, right, T at 5, the height is, okay, does it make sense that it would look something like this? All right, we passed all our tests. And we can calculate the final velocity, right, at that 50 altitude. At T is 5, we can calculate that velocity as a check. And here we can just do it as, in this case, backward difference, because we don't have y plus 1. And we get 32.05. The analytical answer is 34.5. Why is it different? Order of approximation is 1, but it's not the big one. Anybody else? What does the accuracy of finite difference depend on? Step size. Okay, let's up it. N is 100. Why did I redefine it here? That was dumb. Oh, because I never needed to define it up there. Yeah, that would do it. Okay, N is what? Live demos, man. Never do live demos. What's the problem here?
I think you passed n as a different value to the function.
Did I?
Like you have
that would be. No, I've got 10.
n equals
I've got 100
10.
up there.
No,
Yeah.
no, but A, B. Like the line after that.
Oh, yeah. Oh, God. All right. There we go. Live demos, man. Never do live demos. Okay. Our function still works. It was super simple. Let's calculate the velocity. Much better, right? Let's go more. Engineer, if it ain't broke, it don't got enough features yet. Let's run it again. Calculate the velocity. Are we perfect yet? Answer is not yet. Okay, let's do more. You know that Star Wars thing, more, Kylo Ren? I want to try and find the meme and then put that in, but I got lost. All right. What's going on here? Right? There you go. Because, not you, somebody else, why is it still spinning? Can't answer your own question. It's the algorithmic complexity of LU for a dense matrix goes with N, right? And that is the problem. But as we noticed before, this matrix looks like a sparse matrix. And what do we do with sparse matrices? We can, you got it. Let's see if I actually remember this command. Look at that. If I don't remember it, Gemini does. Ba, 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 ba. No problem. And I think we can actually go up in order too, but again, we're running out of time, so I'm going to blast off ahead here. Yeah. So again, LU, good. Sparse LU, good. Engineering, man. You're in engineering physics now. You got it. Okay. Next question, Neumann boundary condition. So Dirichlet, you say this is the value over here. Neumann condition, you say it has no slope. Very, very useful for engineering because no slope means no flux. Any kind of heat transport, if you have insulation, you are doing a Neumann condition. The third type of boundary condition is called a Robin condition, and that's a mix of the two. Whoop-de-doo. So stuff like radiative heat transport. For example, your flux depends on T to the power 4, right? That would be considered Robin boundary condition. We're not going to worry about that. Use finite difference to solve this linear boundary value problem. Okay, we've got the second derivative, we've got the first one over here, and we've got our boundary conditions. Y at 0 is 0, and the derivative at pi is 2 is equal to 0. So our slope is 0. Dirichlet condition is simple. We already did that. The interior points are a little bit messy. Just remember all of your terms of your unknown variable go on the left-hand side. So is x known or unknown? It is known, so it goes on the right-hand side. Keep that on the right-hand side and you'll be fine. Okay? With the Neumann condition, it's actually super simple because we know how to do finite difference. So we look at that and we say, well, okay, we do backward difference because we're at the end, and we say the difference between that value and that value divided by h is that. Okay? We put that into here. This is our matrix. I'm not going to go through this because we're out of time. And let's see how the answer compares to the analytic answer, which is that guy. It's actually wrong in the textbook. Yeah, and this is our answer. And it's super easy. Finite difference is awesome. When you can get away with like an evenly spaced thing, it's super awesome. The problem with finite difference is what the heck is going on down here? Because we said that it should be 0, but you can see that it's not actually 0. It's a little bit sloped here. One thing that I'm going to skip, no, I shouldn't skip this part. The problem is, so they're, yeah. Order of accuracy is one thing, but again, it comes down to the mesh size. So dealing with the first part first, there is a trick with Neumann conditions. What you do is you take the central difference of the endpoint, right? And the backward one exists, the forward one doesn't exist, but you use it anyway. And you get this nice equation that basically just says that if it did exist, it will be equal in value to the previous one, which makes sense. And then you put that into your interior equation. It's a little bit of a trick. But by doing that, because central difference is second order on the endpoint, and you still got the central difference on the interior, then technically it's central difference. Yeah. Yes, exactly. Yep. Okay. So yes, it does work. It is a higher order of accuracy, but it still falls down compared to a finer step size at that boundary. This is the downfall of finite difference. If you have everything that's interesting going on at one boundary, which is quite frankly a lot of the time, right? Like electromagnetics, everything is a skin effect. Everything is right on the surface of the boundary. If you had to measure, so in order to resolve that skin effect, you need super, super small things. But if you are like doing a calculation for the whole domain, you're going to have to repeat that step size. It has to be evenly spaced all the way along. And that's going to be super complicated. But that's the only way that you're going to get away with finite difference. I'm going to stop here because we're out of time, and I just want to hammer that one home a little bit. I'll start on here again tomorrow, and then go into the assignment review, because this is the cool part. One of the big differences between finite element and finite difference is that you can do whatever element shape you want wherever you want it. So finite difference, it has to be that regular grid in order to get all these efficiencies. Finite element doesn't have that. You can make it as small as you want wherever you want it. And that mesh refinement, that targeted mesh refinement, really has a lot of merit to it. There are a lot of other benefits to finite element. That's why that's actually the de facto. But like finite difference, people have literally done this in Excel and published their work based on finite difference done in Excel. Like it's completely possible. Okay, I'm out of time. So I'll pick up here tomorrow, and then we'll go into assignment review. Spoiler alert, the nonlinear systems ends up using our root finder. So I'm actually just going to pull up SciPy root find, and we're going to do this for nonlinear systems. Super simple. Like honestly, just like shockingly, like this is what we've been building up for this whole time, right? Like why are we doing linear system with all the lighting? Here, this is the reason. Yeah. It really is. This is everywhere. You guys are definitely going to be running into this at some point in the future. Cool. Have a good night, guys. What did we talk about yesterday? I think we wrapped up on the higher order accuracy boundary conditions. So this was this little trick that we do I need to go back and review, guys, or should I just continue on ahead? I'll just continue ahead. Okay, so this was the little trick that when you have a Neumann boundary condition, because it's fairly straightforward, you're already at like the endpoint of your domain. So you're at your final element in your vector. So you shouldn't be applying central difference because there is no n+1. But you can use the finite difference formula, the central difference formula, to say it as if there is one. In which case you just get that super simple equation. You plug that into your central difference one that is valid for the interior point, and you can still use that. In which case you get a slightly better answer. Guys that just jumped in, there's a Nuclear Now event in the Alumni Hall. I just came from it, and I'm going to go back there later. It's a bunch of like nuclear industry people. So if you do want to vamonos and go over and jump in that one, what we're going to be doing, I'm just going to wrap up this lecture, and then we're going to go over the assignment. So feel free to stay, feel free to go. I won't take it personally. Yeah. So the idea is that when we do this, right, what we see is, unsurprisingly, n+1, which doesn't exist, is equal to n-1. We plug that into our interior point equation. We put that into our matrix. So now this bottom line is 2 minus all this fun stuff versus just the backward difference formula there. And it gives us a little bit better accuracy. So I don't think this is going to work because I haven't, well, let's see if it works. I haven't run the previous ones. Thinking. Nope. Alrighty. Bear with me a second. Yes, execute. Yes, execute. I know there's an evaluate notepad, but that's boring. All right. So this is the old method where we're just using the backward difference. I should have called it backward difference instead of old. This is the new one where we're using the symmetry because of the central difference to plug it into the interior method. And what we get is theoretically a better answer. Practically, if you look at this closer, it's actually a little bit worse. So I don't have a good explanation for that one, except that don't always trust the theory. And here's your true answer here. It's nice to use these higher order methods, especially at the boundaries. To be entirely honest, your step size dominates everything. If you get the higher step size where you need it, then your answer is going to be quantifiably better. And this is like the big motivation for using something like finite element method, because with finite difference, you need equally spaced data, right? Equally spaced grid sample points. But if you only care about something going on at the boundary, then you're having to refine all these different all these different grid spacings all throughout your interior domain where nothing really important is going on, right? With finite element, you can do the dynamic mesh sizing, so you can concentrate all of your interest, all of your meshing right at that boundary of interest, which is kind of nice. But we'll get to that in a couple weeks' time. Okay, nonlinear systems. I should have said nonlinear differential equations. I guess I just gave that away. Okay. Solve the boundary problem here. Second derivative is equal to minus 3y times the first derivative. So it's extra ugly. We're going to see that finite difference just kind of powers through it. Okay, we've got a boundary conditions here. They're Dirichlet, and they are easy to put in. You just say that the function is equal to that at that point. And then you write this down, again, in terms of finite difference. You get this form. But now the problem is that you have yi times yi plus 1 and minus yi minus 1, right? So now you get this function here where you don't have linear separation of your unknowns, right? What do we do when we have a linear system, we can throw LU at it. What do we do when we have a nonlinear system? This is also review, by the way, right? Solve a nonlinear system of equations. What are we doing here? Nonlinear root finding. Bingo. All we need to do is move everything to one side. Now we have a vector. Now we have a vector function. Digging pipe. Whatevs. Okay. Move everything onto one side. And now what we have is a function, which is a vector, of our vector of unknown is equal to 0. And we know how to solve this. This is just nonlinear root finding, right? We say that that function is the residual, and we find the root where it's equal to 0. And this actually becomes very, very easy to solve, right? F mess. Okay. What we have to do is the same idea that we're still writing out what that function is at every point, right? So this is how we define our vector function. We treat the boundary cases special because boundary cases are special compared to the interior points. So we say that R0 is 0, or excuse me, is just that because that's equal to 0. If this wasn't equal to 0, if that was equal to 1, then that would be y at 0 is equal to 1, right? We say that our last one, which is our other boundary, is equal to 1. That's this guy. Remember, -1 means that you're moving to the end of your element. And in the middle, we put in our finite difference formula, which is this. Goes in super simple. We don't actually need this 2 here because we can factor things out. And then we discretize our problem. We say that we have n different steps, or excuse me, the total number of steps is n, right? We do our linear space, and then we throw root. right? Root just finds the root of this vector equation, root of residual, starting at, remember with root finding, we need to give it an initial guess because it's going to iterate on this. And this args function here is passing arguments into the residual. So the way this works is that the root is expecting a function. The first argument is whatever you're trying to minimize, and these other ones are the argument. So you pass the number of steps and the step size, right? That's not so important. You could also hardwire that in. I just left that in so that you can see the structure of how that's working. And when you run it, it gives you a bunch of data and it solves, right? If you look at this, yeah. So what this is doing, this function residual is taking a vector argument, your vector of unknowns, which is y, and some parameters. Don't worry about the parameters. You could hardwire them. And then it's saying, okay, from your vector of unknowns, we need to calculate the vector of residuals. So what it's saying is that you have a vector. So it's declaring a vector, first of all, that is n plus 1 long, because you need the boundaries, right? So if n is 10, then you need 11 because you have the first one as well as the last one, right? It's saying that the first one is always just going to be y naught, because y naught should be 0 at the solution. The last one should be y at the end minus 1, because that's the boundary condition here. And then everything in the middle is going to be this nonlinear function of the interior y values, according to this equation. Central difference. This is quite literally the central difference, right? So all you do is you take that, you express y double primed in terms of central difference. Y is just falls straight through, and y prime, this is this is second order central difference, this is first order central difference. And you don't have to do anything else for this. And this is really nice. Now, does that make sense? Kind of? Yeah. It's a little bit weird because we're you kind of used to thinking about like a function of a vector, right? Obviously it has to be a linear system because what else are you doing a vector for? But it's not like that, right? Consider the vector just to be a list of unknowns that just so happen to define y1, y2, y3, y4, y5, and does some kind of mixing and matching in between. Okay? So it's kind of, I think we spoke about this, right? The difference between vector and list. I kind of use them interchangeably, and technically they are interchangeable for almost all situations, but it is a little bit of a weird way to think about it. What method is root using? Doesn't matter. Who cares? Right? For our purpose, who cares? It's a root finder. I don't care what method it's using. Normally, when you're doing this, you would be using Newton, because Newton is the fastest convergence, right? Newton-Raphson, right, is going to have quadratic convergence when you are close to the root. Typically, you will have some idea of what the solution will be, especially when you're doing time stepping. Your initial guess is probably what the previous time step was. So you can get in there, you can do quadratic convergence. That's great. The problem with Newton-Raphson is that it needs the second derivative. It needs the derivative. It needs the Jacobian. Because you have a vector function of a vector, what you have to do is the vector derivative, and that's going to give you a Jacobian. Most modern software will calculate all this stuff symbolically. So this whole like finite difference thing is super algorithmic. That's not only is it super powerful, but it's long and it's arduous to calculate yi plus 1, yi minus 1, right? You slam that into a computer and it just chews through it. It very easily, you can identify where your boundaries are. You treat those accordingly with your edge order parameter, whatever you want, right? It's to the point where all you have to give these tools is your function, which is this guy here, and it'll do everything else auto-magically, which is awesome. Including most software will also be able to do the symbolic differentiation. And it'll do that so that you can get that Newton quadratic convergence. We don't want to do that. I don't want to do that. Nobody wants to do that. So let's just use root. And this one is using the hybrid root finding method. And I had to look that one up. It's one of these combinations of the central difference along with, I think it's Powell's method for root finding. But it's like, it's one, like, I don't expect you guys to know that. Hint, hint. Right? Upcoming midterm exam. I would rather you guys know what the difference is between these types of root finders than all these guys' names. That to me is not interesting. The fact that Newton-Raphson is quadratic convergent, that's why it's known. But it requires the derivative. If you have the derivative, great. If you don't have the derivative, don't use it. Yeah, I think it was an adaptation of Powell's method that I didn't talk about in this one. But it's the same idea that you find the conjugate gradient based on that algorithm, but now you're applying it for root finding. Yeah, yeah. It's one of those, like it's some adaptation that wasn't one of like the fundamental set of functions, so I didn't bother calculating it, but I didn't bother talking about it in the lecture. Bum, ba, bum, bum, bum. Here's the solution, by the way, if anybody cares. I don't think anybody cares. Any questions? The whole point of this entire course is feeding something into a linear system. That's what it's doing, right? Everything complicated can be broken down into linear systems. Everything that we've talked about so far, polynomial curve fitting, those are linear systems. You want to do radial basis functions, those are also linear systems. Least squared minimization, that's a linear system. Finite difference, that's a linear system. Everything is linear systems, and linear systems can be broken down further, and that's what LU is doing, right? That's why everybody says linear systems are like the heart and blood of numerical methods. They are the fundamental, and if you get those, you can do everything else. That's the point. All right. Speaking of which, multidimensional functions. We talked about, I guess that would have been yesterday, that the finite difference is super trivial to get to n dimensions. All you have to do is say, yeah, it generalizes super easy. The components of the gradient. So if you want to do the gradient of the function, that's just di-f by di-x. That's di-f by di-y. And we know how to do these. We already know central difference, so you just calculate it component-wise. Same thing with the Laplacian, right? All you have to do is di-f by di-x squared. We know that one. We know the mixed one. The mixed one is super simple. All you have to do is take that way and then that way, and you get a formula for that one. We don't have to know that one. It's super easy to get. And then you can calculate this. So if we have, and you might recognize this one, solve the discrete Poisson equation on the unit square, right? This is the second derivative. It's the Laplacian operator. It's equal to a source term. We have u is equal to 0 along the boundary. Dirichlet condition, very easy, right? And we put that in. This is the expression for the central difference of the Laplacian. So this is a second order, and it's literally, you can see, right? So what we're going to do is this. We have our unit square, just like we discretized time in one dimension. We're going to discretize space, two-dimensional space, as a rectangular grid. Square grid, not rectangular, square grid. Yeah? So that means that we're going to do one of these and we're going to do one of these, right? This is a little bit weird, so I do want to show you this. I should have put it into the notes. I didn't have time, right? So what we're going to do, just like up here, what we did was say y0, y1, y2, dot, 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 dot. This is going to be u, 1, 1, or well, actually 0, 0, right? U, rows, columns, 0, 1, u, 0, 2, dot, 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 right? U, 1, 0, U, 1, 1, da, 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 right? So what you're going to get is now a matrix of unknowns. The problem is that matrices of unknowns doesn't fit into vanilla linear system solvers. In fact, it does. There are linear systems where X is not a vector, it's a matrix. A then becomes a 2 by 2 by 2 by 2 operator, and you can actually still solve it in an analogous way, but nobody does that. It is possible. It is still considered a linear system. Nobody does it because it's ugly. Okay? So instead, what they do is they unravel this matrix. And what that means is that you take this, move it over there. You take this guy, move it on to the end. You take this guy, you move it on to the end of that one. And what you do is you take that matrix, you split it up, and you make a long vector. And the rest is bookkeeping. Right? So if you wanted to index this particular value, what you would have to do is take, what is this? U 1, 2, 3, 3, 1, oh, sorry, 1, 3, right? What you would have to do is calculate where in the vector that was. So that would be n times that index, n dot 3 plus whatever that one was. Oh, sorry, n times 1 plus 3, and that would give you the index of the vector. Like all that is like the algorithm side of it, right? Feel free to work it out by hand. Honestly, ask Gemini to do that. But what you get then is this nice code here, right? So there again, you're calculating your step size. You're defining your matrix. Note your matrix is now n plus 1 squared. Because if you're doing a step size of whatever, you have 10, 10. So now your vector is actually, sorry, now your matrix is actually 100 by 100. By a little bit more because it's not 10, it's 11. Right? Similarly with your vector of constants. And then now we're actually finally able to read this thing, right? So what you do is you look for your boundary cases. So what this is doing is it's stepping through all of the x coordinates and all of the y coordinates. This is a nested loop. It's saying if I is equal to 0, which is your left boundary, or I is equal to n, which is your right boundary, or j is equal to 0, or j is equal to n, which is your top and your bottom, then treat it specially. And treating it specially means Dirichlet. So all you have to do is put the calculate what your row index is. This is going to be along your direct diagonal, and you just put in a 1 there. That's all it is for Dirichlet. And for your interior points, this gets a little bit trickier. Not a little bit, this is actually quite a lot trickier, but it's all algorithmic, right? What you have to do is translate your row column into position in the vector. And you got to play around with that a little bit until you internalize that. But once you get it, it works for all of them, right? It's a super simple thing to unravel that. You just have to keep track of your numbers. And then you apply your central difference formula to it. Second order central difference. Let print A, right? So this doesn't actually look very useful. Instead, what we can do is look at the sparsity pattern of it. We already dealt with this one too, so this shouldn't come as a surprise. But this sparsity pattern is because we're taking, like you have your central you have your main diagonal, obviously, right? You're taking the ones in front and behind it. And then n all the way over here, which is the one above, and minus n all the way over there, which is the one below it. And that's why you get the banded matrix. And what do you do once you have that? You solve it. Lin out, solve, which does LU. And what do you get? You get your super faceted Poisson equation there. But all you would have to do if you want to make that a better approximation, here I go with live demos again. Let's try this. This is going to die because I think that has to be, well, okay, banded matrix, right? What kind of LU should I be using? Right? I didn't bother putting in sparse because I got lazy. Sorry. But all you have to do to increase the resolution for that is just increase your sampling frequency. And that's it. If you want to do 3D, exactly the same thing. If you wanted to do 4 dimensions, any dimensional space, it doesn't matter because it's super algorithmic to put into this thing. The big downfall is still how you get the mesh resolution where you need it. Once you've got that, and that's kind of like one of the big motivations for finite element. Yeah. There are other ones. Nice thing about this is that it's so simple. I've seen people do it for Excel. Right? Somebody's actually submitted a journal article that I had to review where they solved something called the phase field model, which is what I do in Excel, and showed the result. And I was like, yes, you can. But like Excel isn't really optimized for that. So it's kind of like, yes, you can. You could also do a paper and pencil, technically. You shouldn't. But anyway, long story. Any questions about finding a difference? Okay, we're going to come back to find a difference because we didn't talk about time stepping. And time stepping is actually a pretty big problem. But that's for maybe next week? No, integration is next week. Time stepping, I think, is the week after that. Yeah. Any questions about that one?